Action. Okay, the goal for today is to understand linear operators. The first thing I'm going to do is look at what some of the operators are and then the properties of the operators. But let me start by, even before this, saying what comes on a later slide. The point of operators. It's kind of good to know the point of the operator before you start doing stuff with it, just because then you understand what it's good for. You know, I can explain things to death, but if you don't understand why they're being pointed at, it's kind of hard to pay attention to, even much less to master it. So the operators are our mathematical way of extracting observables from a wave function. So what we've learned so far is the wave function is a function that describes as is correctly termed in air likes to call it a matter wave, which it has all of the information we have about that quote particle, but we're treating it as a wave. Operators then are functions that will extract the important observable things from that function. So it's kind of like you have a computer, and the computer has all of this data, and you've got to make a query to get the specific thing, like what was the temperature on July 3, 1987. You've got to make your query, and then it will give it back. So observables are called observables because they're actual measurements. They're actual values. So observables are going to be things like position or momentum or kinetic energy, things that we can measure, things that are real values. They have to be real, because real things are real. That's kind of what real means. So the wave function is complex. It has real and imaginary parts, but the result from the operator, the observable, has to be real. So the operator is a function that acts on another function and will return an observable value times the original function if it is an appropriate operator for that function. Yes.
So the entire result needs to be real, or just the value in front of the original function?
Just the value in front of the original function, right? Because if the original function is complex, then that part will be complex.
Okay.
So that's the purpose of these operators, to extract the information. And I've already given you the trivial one. If our wave function, looking up the first few slides, the color combination is poor. I imported and told to use the same theme, and it wasn't the same, and I didn't have time I could have changed the color. I didn't realize how bad it was. Sorry. Anyhow, the trivial one, if we have our wave function in position space, that is if, the wave function doesn't have to be a function of position. It could, for instance, be a function of momentum in time. But if it's a function of position in time, then the x operator acting on psi of x and t must give us, by the definition of what the x operator is it better give us the value of x multiplied by psi x comma t. So if our wave function has x as its variable, then it better just give us the value of x. If it had momentum as the variable, it would have to give us a function of momentum that's equal to the position, right? So it'd be like p divided by m times, something that has some funky stuff in it, so that it's going to have the right units for position. So that was our first operator. The second operator is finding the momentum operator. So to find the momentum operator, we start with, and this is on pages 16 and 17 of the textbook, I said, although if I look at it carefully, it's on 15 through 17, because it starts on page 15, really. If we want to find the momentum operator, we start by saying, okay, if I'm going to find momentum, I need to find mass times velocity. And velocity is kind of problematic because if you're talking about a particle, that's easy. This thing's traveling with a certain velocity. But if we're talking about a wave function, we're talking about a particle that is in various states, and how do you get velocity for these various states? So it's not quite the same idea as the velocity of a simple particle. But mathematically, we're doing the same thing. So we're going to take velocity, speed, since we're one-dimensional, so it doesn't matter, should be dx dt. But we don't really have a fixed velocity, so what we're really going to do is the expectation value of velocity should be the time derivative of the expectation value of position. So that's the first start, and then we're going to say momentum is equal to mass times expectation value of v, and then from that we're going to take the definition so that's the process of finding the momentum operator. So we have to go through the steps. We have to find what the derivative of the expectation value of position is. Do you have a question, Erin?
Yeah. So in practice, do we usually have the operators acting on the integral of psi mod squared dx? Is that
No.
Okay.
No. The operators act on psi.
Okay.
Sometimes you'll do funny things, like have the operator act on psi star and that kind of thing. But fundamentally, the operator acts on psi. So going through the process, and you can follow the process starting on the bottom of page 15 in the textbook. You have first, okay, so what's the derivative of the expectation value? We have the derivative with respect to time. It's an integral of position, so we can bring the derivative with respect to time into the integral. But once we bring it in, just like when we did before, it needs to be a partial. And I went through this on Wednesday because I thought, I don't know why I was never going to get to it on Wednesday, but I thought I was. And so I didn't go through the derivation carefully again today to make sure I'm up to date on it, because it's not super, super simple. The method, yeah, they go through things rather quickly here. If you look at equation 1.29, you have the integral of x times the partial derivative of psi mod squared dx. And that, at least to me, would seem odd until you remember it's a partial derivative. So if it's a partial derivative, you don't have, d dt of x is 0. And so that's why the x can move through. So let's just start and do the whole thing. That would be writing out the first step in its most basic form. Is everybody with me on that? And then the next step was to recognize that what do we get when we have x operator acting on psi? Right. And so we can rewrite this as d dt of integral. And now that we have x, the x can move around, of x psi mod squared dx, where I combine the psi star psi because they were next to each other now. And then that exact differential of the integral must become a partial when I move it inside. So I made it a partial when it moved inside. But then because x is not t, then I finally can get to what they have as the second thing written. of this. Now in your homework, I'm pretty sure both of you have already done problem 1 for the homework that's due on Wednesday. And so for problem 1, you had to do exactly that, right? And so when you did that, you got the next step then, just taking the result of your work from that homework problem. So that gets us the first equation in the derivation. And of course, we skipped a few lines there because you've done it in your homework. So once you can see there's a whole lot packed into what looks like just a simple equation.
Are you missing a psi at the end?
Am I missing a psi? Yes, I am. Okay, so I mean, I want you to recognize when you look at equation 1.29, you shouldn't just be saying, oh yeah, of course, right? It's not an obvious equation. It's an equation that there was a lot of work that went into. So once we have this, then we're like, well, what do I do from here? And of course, the textbook tells us now we integrate by parts. So who likes integration by parts? All right then. So we're going to be happy or people at this. So integration by parts. Of course, I have to turn to the next page. So I'm just going to actually, fortunately, since this is what we had, I can rewrite it without having to refer back in my notes. Okay, so there's our equation, and we have to define a u is equal to x. Therefore, du equals dx. That's pretty simple. And that leaves dv is equal to ddx. And I'm just going to put a big parenthesis here to represent all that stuff. dx. And so if that's dv, what is v equal to? Oh, wait, no, that was right. That was right. Once again, we refer to the fundamental theorem of calculus. Yep. So it's going to be that parenthesis dot, dot, dot. So now I have my u and my dv, and I've calculated my du and my v. So now integration by parts. I meant to change colors. It's uv minus the integral of v du. So that's going to be equal to x times psi star d psi dx minus d psi star dx psi. And remember, there are actual limits. I haven't been writing the limits on this integral, but what are the limits for the integral? And then I'm going to have minus the integral of v du oh, crud. I forgot this I h bar over 2m in everything in everything below. So I'm going to erase this just so it's so that I don't have to worry about the I h bar over 2m and can put it in later. That's there. So integral psi star d psi dx minus d psi star dx psi dx. The first one is simple. Why is the first one simple?
Oh, you're just reading.
The first part, this part here. What is psi of infinity? Required if it's going to fit Schrodinger's equation, if it's a solution. It must be 0. So what does that make this when I put in infinity and minus infinity? That whole thing has to be 0. So everything here has to be 0. Yes, I can. So if we take this, we're going to have, when we put in the limits, so I'm only looking at this term here in this box, okay? The box needs to go farther down. So if I put in the limits, I'm going to have, put in the upper limit, infinity times 0 times 0 minus 0 times 0 minus, parenthesis, minus infinity times 0 times 0 minus 0 times 0. We have infinities out front, but then we have times 0. And while I know infinity times 0 is indeterminate, it has to be 0 because the size have to go to 0. And so even though we have these x's here that are troubling and we'd have to use L'Hopital's rule to actually evaluate it, we use L'Hopital's rule and it's going to come out 0. Well, it's not that uv equals 0, it's the integral. There, it's the uv evaluated minus infinity and plus infinity is 0. Because that's what that really is, right? You have the evaluation. And so I'm sorry, I should have put the evaluation things there. So that's all 0. And so we just have to worry about this negative integral here. And so we'll break that up into 2 integrals. And what do we do with that? I'm pretty sure we do integration by parts again. Yeah. We do another integration by parts. And actually, I will only do an integration by parts of one of them. Why only one of them? Because if I do integration by parts of this one, it's going to give me that one. And so let's do that integration by parts. And you can see the similarity already. Since u is psi, du is going to be d psi dx dx. And just as we saw before, since dv is d psi star dx dx, then when we integrate that, it's going to be v is psi star. And so doing the integration by parts, integral of d psi star dx psi dx must be equal to psi star psi evaluated minus infinity to plus infinity minus integral of psi star d psi dx dx. And who can tell me what the value in this blue box is? 0, because when we put in the limits, at the limit, that's 0 times 0, whether it's plus infinity or minus infinity. So now we had minus integral of psi star d psi dx dx plus this, which is again minus integral of psi star d psi dx dx. So what we have arrived at now is and now I'm going to write down this term that I haven't been writing, the I h bar over 2m. Minus 2, because the first one and the second one are going to add to give you 2 of the same thing. Minus sign, because notice there's a minus sign right here and a plus. That makes it a minus, and this was a minus out front here, so that's why it's a minus sign. We are only one step away from being done with the first part of the derivation, which is the long part of the derivation, mind you. And that is recognized that 2 and 2 cancel. Yes, I can, and we do that a lot. So here's what we found. The time derivative of the expectation value of position is equal to minus I h bar over m integral of psi star d psi dx dx. Now let's go back and remember why we did this. So going back to our strategy here, the first thing we did was we found the expectation value for velocity. That's what we found. And now we're going to say, well, expectation value for momentum is m times that. So that stars. So that's our expectation value for position we found, and thus expectation value for momentum. So there's the expectation value for momentum. And now we can make the last step. This has to equal, by the definition of an operator, the integral of psi star p operator psi dx. So I'm going to rewrite this, bringing everything into its right position. X, now I put it into the operator. So the ddx is acting on psi. So when it acts on psi, we're going to get d psi dx. And now we can read what is our momentum operator. And like I said, we write it the second way that Aaron asked about often. Just because it doesn't have a minus sign, but it has a divider. So did you really gain anything?
Okay, so all operators, is the momentum operator considered a linear operator?
It's a linear operator, but it turns out that the momentum operator is not one that we can use. It's not one that we can use because it's going to change our wave function. It's not going to get us back to the original wave function. And so you might say, why? Why did we do this? Well, here's a starter. We did this because we want to find the kinetic energy operator. And kinetic energy is 1/2 mass times velocity squared. Well, in terms of momentum, since momentum is mass times velocity, I can write velocity squared as momentum squared divided by mass squared. And so that's the term in between here. And so we'll have momentum squared, mass on top, and mass squared on bottom. So it'll be over mass in the end to give us p squared over 2m. And then we just say, okay, kinetic energy operator is momentum operator squared over 2m. And so we take that momentum operator, p operator squared is equal to p operator acting on p operator. Actually, it'd be, well, I'll show you that in a minute. So I times I is -1, minus times minus is plus, plus times minus is negative. We end up with a negative. H bar times h bar squared, ddx of ddx. And I think I said this before, but just to make sure you recognize, the reason we put the squares in different places on a second derivative is kind of clear when you do it this way. You have a small change twice on top, divided by a change in x times a change in x on bottom. You can have d second f dx dy, two different things on bottom. But it's because we have dx times dx. That's why we have dx, the whole thing squared on bottom. So this here, and that's P operator squared. And so the kinetic energy operator is going to be that divided by 2m So there's our kinetic energy operator. So now finding the momentum, even though we're not going to use the momentum operator too much, we will use it, don't get me wrong. It's just it's not going to give us back our function. We will still try to find the expectation value of momentum and things like that. But we can get the kinetic energy operator, and this one here is going to be fine. It's going to work with our psi, even though momentum didn't.
Why? It's still
Well, looking at it from a simplistic point of view, if you have a sine function, the first derivative of the sine function is a cosine function. That doesn't work for you. But the second derivative brings you back to a sine function again. That's the nuts and bolts of why it works.
So by finding the momentum operator, you said we'll do that sometimes. Is that just an intermediate step to finding the kinetic?
No, we're going to in just a minute. I'm sure we're not going to get to it today, but I have in today's lecture in case we do. When we get to the uncertainty relation, we want to find the uncertainty in momentum. Well, to find the uncertainty in momentum, you have to find the expectation value of momentum and the expectation value of momentum squared. And we'll still go ahead and do that. We'll be doing it with the Gaussian function. And with the Gaussian function, it actually is not a problem. Okay, another one that is going to be important to us, but not this chapter, and I don't think the next chapter either, is angular momentum. Angular momentum is R cross P. You probably don't need to write anything down on this because this is a three-dimensional operator, and right now we've only been working in one dimension. So in one dimension, you don't have angular momentum. So we're not going to do anything with it. Just pointing out that at a later date, here's another place where it's going to be useful. And we'll find out some pretty bizarre things there. The outcome will be that we can have any one of our three angular momenta will work, but not the other two. And angular momentum squared will work. And that leads us to things that you may or may not at this point tie together. But you know the quantum numbers that we have for an atom? We have N, and we have L, and we have M sub L and M sub S. The L is the one that has to do with the angular momentum squared operator. And the M sub L has to do with the one direction we arbitrarily define as the z direction of angular momentum that we can have it work with.
Oh, okay. So you have to specify both the angular momentum and then the...
Yeah, because the M sub L, okay, the L is telling you the total angular momentum. Because what it really tells you is angular momentum squared, but all you have to do is square root the angular momentum squared to get the angular momentum. So the L tells you the angular momentum. And then the M sub L tells you the orientation of it. It specifically tells you how much is aligned with the z-axis. So it could be going like this, or like this, or like this. It's telling you how far it is from oriented with the z-axis.
Okay.
But you still have the x and y that it precesses through. That's part of it doesn't work with it because it's actually going to change. And we'll learn all about that. Just precursors, things to help you tie together. There's actually utility to this. It's not up there just rambling about things that will never make sense. Hopefully that's not how you feel. Okay, now we've gone through to see how we get the momentum operator, and I personally find it annoying, the process of finding the momentum operator. learning rules about operators and how they work, that's really important. So notice my first line here, it's a mapping. It's, like I said, with the computer has all the information, you have to draw it out, and the operator is what draws it out. We have our wave function that has all the information. That wave function looks very simple, and yet it's very information dense. And the operator is what brings it out. So it maps between two vector spaces, the vector space of your wave function and the vector space of your observable. Operators, they do not always return the same function, but for us to use them in quantum physics, we need them to. And so you have an operator, and a function is a function of the operator. If the operator acted on the function, gives you a real observable, which we call an eigenvalue. So when I start saying eigenvalue, don't get freaky. It just means the observable. It's using German words, an eigensystem, where you have eigen one or something like that. You have, for each function, you have a state. The operator acting on an eigenstate gives you the eigenvalue times the original eigenstate. It's the terminology we use. So we have to have the operator act on the function gives us a real value times the same function. And then we have two questions here. Is the wave function shown up here a function of the momentum operator, and is a function of the kinetic energy operator? I've already told you the answer, but now we're going to do some work just to see. So it's going to be a function of the operator if you get the operator back after doing the work. So here's our wave function we're going to test and the two operators. So if everything is kosher, I should have P operator acting on psi is equal to P times psi. So let's translate that. My P operator, here I forgot, I went through and tried to change these, but I did not notice that I had the little hats there. Those are the operators. So putting the P operator, I would have minus I h bar d dx acting on a sine of kx equals, and we just calculate that. So what's the derivative of a sine kx dx?
Cosine kx times k.
Okay, we have to not forget the a times k cosine kx. So it's just bringing out all the constants into one thing, minus I h bar a k cos, oh, actually the a needs to stay with the function. And we see we have a problem. We have a problem because this is a cosine, but we started with a sine. So one would look at this and one would say, well, it has an eigenvalue of minus I h bar k, but it's not a function of the operator. So it doesn't really work.
I thought you said it needed to be a real value.
It does.
So is that another reason why it doesn't work?
That would be another problem here, yeah. Yes, that would be another problem here. So that one there, the answer is no. And now we test the next one. Kinetic energy operator acting on psi should be equal to kinetic energy times psi. So that would be minus h bar squared over 2m d second dx squared a sine kx. So what's the second derivative of a sine kx dx? Or second derivative, and I said 1 dx. Second derivative with respect to x of a sine kx. First derivative was ka cosine kx. What's the second derivative?
The negative AK sine kx.
Okay, we're gonna have k squared
Yeah,
because k for, negative k squared a sine kx. So now if we combine the terms out front, minus times a minus is a plus, h bar squared k squared over 2m. And so now we see this one here, the wave function is a function of the operator. And what's the eigenvalue for this state? What is the observable energy? Yes. I just want to make sure that we're making that connection, that there is the kinetic energy. All right. Now, this is where I plan to spend the bulk of the time. We only have 8 minutes. Hey, good. We'll pick up with this next class period as well. What we're going to do now is we are going to learn how to check to see if an operator is a linear operator. I was reading up on this before class because that's what teachers do to make sure they're up to date. And actually, in 1998, physicists realized that your operators don't have to be Hermitian. How many people know what a Hermitian operator is? Well, this weekend you don't have to learn it that early. Okay, it's Hermitian operators. As far as we're concerned, they're the ones that give us real results when you put them on a function. And so that's why they have to be Hermitian, because we need to have real results. And the definition of Hermitian we'll come up with, or we'll work on later. Notice it says, we will discuss this later. And they need to be linear. Now, like I said, in 1998, they realized there are some other operators, like the, time parity operator, that technically are not Hermitian to give you only real values. So it doesn't exactly have to be Hermitian, but as far as we're concerned, we're going to stick with it. We're not going to get to that level. And so we're going to have two behaviors for them to be linear. And we're going to focus on that right now. One behavior is you need to have the distributive property. If I have an operator, so this L hat is my operator, that operator is acting on function of x plus function of x. There are two different functions, that's why it's f and g. It has to equal the operator acting on the first function plus the operator acting on the second function. Not all functions do that. So that's one test. And the other one is, if I have the operator acting on a constant times a function, that has to give me the constant times the operator acting on the original function. Once again, it seems pretty obvious that that should be true, but operators have a lot of things that they can be, and so those are valid tests that we're going to do. So for homework 3, you have 6 different functions, and you're going to go through and check each of these two things to see if that function is a linear operator. Now, they're not necessarily ones we use in quantum physics, even if they pass your tests. The test is to make sure you understand these are properties you have to be linear. So let's get to work. Function number 1. The operator acting on function of x is function of x plus x squared. So by show of hands, how many people think that's going to be linear? I say by show of hands, how many people think it's not going to be linear since no one raised their hand? It's, you said that, think of that. Any gut feeling?
I mean, if it's the distributor, I'm not really sure how to tell.
Okay, well, we'll do the work. That's how we'll tell, right? Right now, you have a gut feeling. Okay, so test one. So there's our test. So I just go through and I do it. So if my entire function comes back the same and I just add a term, then I would have the left-hand side is going to be f of x plus g of x. That's my entire function plus x squared. Right? The thing that was in the print or in the brackets plus x squared. On the other side, I have f of x plus x squared plus g of x plus x squared. Are those equal to each other? No, they're not, because this has two x squareds and this has only one x squared. So
Can you go over how you put that together?
yes. Let me maybe color code it to make it easier to see. So or maybe not color code it. Oh, it's down here under that edit properties, color, blue. That's what I wanted. It shows blue. There we go. And then likewise this here. Okay, so okay, so the blue is the stuff that the operator is acting on. And so my function up here is you have the operator act on the function, gives you the same function, so the blue stuff stays the same, and then you're going to have x squared added on. And so doing the next one, that f of x, operator acting on the f of x gives me the same f of x plus the x squared that you get from the operator. And then my final color change, hopefully this is a color we can read. It's easier just to erase the g of x than to write the whole thing. Right, so the red plus x squareds are coming from this thing that the operator is doing to modify it. And so when I put it together, those aren't equal because they had two x squareds on the right side and one on the left. So it fails the first test, but I'm still going to check the second test. And I'd like you to do this on the homework as well, just to get practice with both tests instead of stopping each time the first one fails. So for the second test, I'm saying if I put a constant in front of my function, is that going to be the same as if I had the constant out front? And so to do the test, I would have O1 acting on AF of x is going to give me whatever is inside of the brackets. That's AF of x plus x squared. Look at the other side, I'm going to have A times whatever O act on F1 of x is, which we know is f of x plus x squared. Are those equal? No, they're not. So it failed both both tests.
It only needs to fail one.
It only needs to fail one, but I want you to test both to get practice on them. I'm out of time. I have 3 of them. If you go through and check, this one here is linear. The other, clearly with the square, is not linear. At least, that one should seem. So I don't have time to go through the other 2 today. We will continue with this tomorrow. Questions before we dissipate?
What would the operator be on the second one?
Well, the operator is squaring the function. The operators don't have to be simple things, right? Squaring it, taking a derivative, taking the integral. This can all be parts of the operators.
Okay. And then on the last one, would it be
It's changing the variable.